Today's discussion delves into a fascinating paper titled The Struggles of Chessland. It's a unique blend of storytelling and mathematical analysis, exploring the challenges of surveying and trapping enemy pieces on a chessboard like Island Kingdom. Intriguing, isn't it?
Absolutely. It cleverly uses a familiar game, chess, to illustrate complex graph theory problems. The authors, a group of young mathematicians, present their findings in a captivating narrative.
The story unfolds in Chessland, located within the Bermuda Triangle, no less. How does this setting influence the mathematical problems presented?
The Bermuda Triangle setting adds a whimsical layer, but the core of the paper lies in the unique constraints imposed on the chess piece's movements. These constraints directly translate into graph theoretic challenges.
So let's start with the surveying aspect. The paper details different strategies for chess pieces to efficiently cover their islands. What are the key mathematical concepts at play here?
The surveying problem boils down to finding the shortest path that allows a chess piece to see every county on the island. This translates to finding a dominating set in a graph, where each county is a node and edges connect counties the piece can move between. The shortest path forming a dominating set determines the minimum surveying time.
Right. The knight strategy involving a shoelace pattern is particularly interesting. Can you elaborate on its efficiency and limitations?
The knight's shoelace pattern is efficient for islands with dimensions divisible by 7. The pattern's effectiveness stems from its ability to systematically cover a rectangular area. However, it becomes less efficient for islands of other sizes, requiring adjustments and ultimately leading to a more complex formula for the minimum surveying time.
I see. The paper also discusses the rook, bishop, and queen surveying strategies. How do their movement limitations affect their surveying numbers?
The rook's linear movement allows for a straightforward surveying strategy, resulting in a surveying number equal to the island's side length. The bishop's diagonal movement requires a more nuanced approach, with the minimum surveying time depending on whether the island size is even or odd. The queen, combining rook and bishop movements, presents the most complex scenario, with the minimum surveying time still an open research question. The king strategy, using a spiral pattern, also presents interesting mathematical challenges, with the minimum surveying time calculated recursively.
The king's spiral surveying method is particularly intriguing because of its iterative nature. How does the paper approach calculating the minimum surveying time for this strategy?
The king initially uses a straight spiral, but later adopts a zigzag spiral due to an unexpected event in the story. The minimum surveying time for the straight spiral is calculated recursively, comparing the spiral paths for islands of sizes n and n3. The zigzag spiral introduces additional complexity, but the paper simplifies the calculation by approximating the zigzag path with a straight line spiral with a larger spacing between loops.
Okay, now let's shift to the trapping aspect. The paper explores how different chess pieces can trap their enemy counterparts without attacking them. What's the underlying mathematical framework here?
The trapping problem involves finding the minimum number of non-attacking friendly pieces needed to prevent the enemy piece from moving to any unoccupied county. This can be framed as a set cover problem, where the universe is the set of counties the enemy piece can access, and each friendly piece represents a set covering a subset of these counties. The challenge lies in finding the smallest independent set cover, ensuring that the friendly pieces don't attack each other.
Right. The paper provides detailed analyses for the knight, bishop, rook, and king trapping strategies. What are the key findings for each piece?
For the knight and king, the trapping number is bounded by a constant, reflecting their limited movement range. The rook's trapping number is elegantly shamed to be n1, achievable using Latin squares. The bishop's trapping number is more complex, with untrappable positions on the diagonals and adjacent cells. The queen's trapping problem is the most challenging, with the paper establishing a lower bound and conjecturing that trapping is always possible for islands of size 5 or greater.
The paper concludes with a discussion of the mathematical implications of the findings. How does the paper connect the storytelling elements to graph theory concepts?
The paper uses the narrative to illustrate key graph theory concepts, such as dominating sets, domination numbers, set cover problems, and independent set covers. The different surveying strategies highlight the challenges of finding optimal dominating sets in various chess piece graphs. The trapping strategies illustrate the complexities of independent set cover problems, with the difficulty varying significantly depending on the chess piece's movement capabilities.
I see. The paper also touches upon the open research questions related to the queen's domination and trapping numbers. What are the implications of these open problems?
The open problems related to the queen's domination and trapping numbers highlight the inherent complexity of analyzing non-local movement patterns in graph theory. These problems represent significant challenges in combinatorial optimization and graph theory, with potential implications for various applications beyond chess.
This discussion has been fascinating. The paper's unique approach of using a captivating narrative to illustrate complex mathematical concepts is truly commendable. The blend of storytelling and rigorous mathematical analysis makes it accessible to a wider audience while still presenting valuable insights into graph theory.
I agree. The paper's success lies in its ability to bridge the gap between abstract mathematical concepts and a relatable context. The creative use of storytelling makes the complex problems more engaging and easier to understand.
Thank you for this discussion.